So it's nice to be back to the Institute after a long time. And what I'm going to talk about is, as you know by now, a practitioner's view of what a high performance computing demands. So I'm from S&I Engineering Solutions, a technology company incubated from IIC. We are the developers of a computational fluid dynamics tool called Hyphen, which is used in a big way in the Indian aerospace and defense industries. So just to give a background, what's computational fluid dynamics? So it is an integral part of an industrial design. So if you look at a slide from Boeing in 2005, you will see a Boeing 787, which is practically designed by the simulations, in particular using the CFD tools. So it has become an integral part of the industrial design. The advantage of using CFD over, say, the experiments is that it reduces the cost of model or prototype testing. So you have a wind tunnel which can span over several acres and would require billions of dollars to build, but the same kind of analysis, you can do it numerically with the help of large-scale, massively parallel supercomputers, which are considerably cheaper compared to these experimental facilities. Another advantage is the CFD codes provide greater physical insight to the designers. So there was a time with the help of experiments, the designers would get some raw data, some basic data, as you see on the left-hand side figure. But with the CFD, you can get the details in terms of the flow visualization, which will allow the users to really, the designers to really look at the areas of problem and then look at the solutions which would mitigate those issues. So I think my previous speaker has eloquently brought out the need for the data centers and the power requirement. Again, CFD is again one of those technologies which is computationally very expensive. For an aircraft like what I showed before, typically we use workloads which are 500 million by 500 million matrix inversion, if you understand what it means. Otherwise, like it's just a large workloads. So it requires massively parallel high-performance computing platforms. We typically make use of 10 to 20,000 processor cores in order to generate the design data in a time frame which is attractive to the customers. These are memory-bound applications. Typically, for solving a problem of this scale, we would require about 100 to 100 gigabytes of data to be stored. The memory access is heterogeneous due to the complexity associated with the underlying problem. We need double precision for accuracy and also for robustness. It leads to frequent cache misses, and the memory speed and bandwidth has always been a bottleneck. So always we found that the speed at which the processor can do the computations is much higher compared to the memory access, and that would always be a bottleneck for us, though the things are changing of late. So when we were introduced to the posit arithmetic by Caligo, it was kind of a revelation for us. So the question is, if we can do the same calculations by using 32-bit instead of a 64-bit, it would be really advantageous to us in terms of, first of all, reduction in the memory requirement. So if you can do what we otherwise do on 64 bits in 32 bits, it would reduce the memory requirement by half. So that means the memory access would come down. It would lead to improved cache utilization, and this would directly lead to a faster single processor performance. This is something which we always look at. Apart from scaling the problem, how do we improve the single process performance? And this is a direct answer to that. This would, from the company point of view, it would lead to a reduction in the capital cost. I know all of us know the memory prices have gone through the roof. And also there would be a reduction in the operational cost, because the power that you give to the HPC gets converted into heat, and then you require air conditioning unit to remove that heat. So that will consume additional power. So with this, I think we started with Caligo with a very, very, I would say, a basic numerical experiment where we sort of solved a scalar convection diffusion equation, which is basically a partial differential equation that looks like that. So we have done analysis for the double precision IEEE as well as the Caligo's PNU 32 engine. And what we measured was the global numerical error as the grid gets refined. So this is a very classical way of looking at the error in numerical computations if you really want to dive deep into it. And what we found was that the POSIT 32 architecture, it delivers comparable precision to the float 64. This also maintains stability and accuracy across the mesh sizes. And this would definitely enable us to power the engineering simulations with a lower hardware demand. And this also kind of enables us to validate POSIT for R&D sectors. So to conclude, the POSIT 32 of Tunga chip on Uttunga accelerator card has delivered us accurate numerical solutions which are at par with FPU 64. And we see potential advantages in terms of enhancement in the single process performance of our software, reduction in the HPC capital cost, and reduction in the operational cost. So with that, I would stop. Thank you very much.